justice, I'll just talk through the first one pretty quick, right? So part C of this problem is the energy bounded, okay? And the question is why or why not, okay? And within the problem, I gave out some trig identities in order to solve, well, in order to compute these integrals. So what's the energy? So can somebody tell me what, I want to know what if the energy is bounded or not. What is the energy going to be?
1/2 the integral of ux squared plus ut squared dx.
Yep. And if I had a non-trivial wave speed, right? If this, I would have to put a c squared there, right? So now you may say, well, this integral is from 0 to infinity. What am I going to do? But remember that in this problem, right, when x is greater than t, I know that u is equal to 0. So that means ut and ux are also equal to 0. So actually, this is only an integral from 0 up to t of ux squared plus ut squared dx. Okay, so that gets me somewhere. And then I actually need to compute these things, right? So u sub t, remember I already got this, is cosine of t minus x, and u sub x is going to be minus cosine of t minus x. Okay, so then the trick is just applying those trig identities, right? So cosine squared of t minus x plus cosine squared of t minus x, right? With a half out front. So these are, that's really messy. Okay, so this is just 2 cosine squareds of t minus x, right? So then I can just combine them. And I get just cosine squared of t minus x, right? I can also make the change of variables like z equals t minus x. And I get the integral from 0 to t of cosine squared of z dz, right? And you can either be given what this integral is, right? Or I can give you the double angle formula, which is that cosine squared z is just going to be 1/2 1 plus cosine 2z dz. Okay, and now we see, right, that if I integrate this up, I'm going to get t over 2 plus sine of 2t over 4. Okay, so this is not concerning as far as boundedness. But this, and basically in the limit as t goes to infinity, my energy becomes unbounded. Okay, so the question is why, right? If I think back to my original PDE, this is now where we have some physical interpretation. What is going on with the original initial boundary value problem that would suggest to me that I should expect the energy to be unbounded?
I guess the boundary condition is feeding energy into the system.
Right. So what's going on here, right? We can even draw sort of a picture of the string, right? Is that I have this string, right? And I'm moving the string up and down sinusoidally, right? So it's like, there's a person or some machine that's grabbing the end of this string and moving it up and down, like a person just holding a rope or something like that and whipping it up and down, right? And if you're continually flowing energy into the string and there's no damping at all, then we should expect that the energy in the string is going to build up. And physically, the energy in the string is, both the deflection or the tension that's built up from having the string um, sort of varying spatially like this, and also the actual movement of the string, which would be the kinetic energy. Okay, so the short answer is it's the forcing, right, that's doing it. Okay. Questions about that?
So it, I feel like intuitively any kind of forcing on the boundary has to put energy into the system, but is that wrong? And if it's not wrong, then how do I mathematically justify that the having like a function h of t that's non-zero can only increase the energy?
Yeah, so another way to do this, right, is to not plug anything in, right? Not plug your solution in. And what you could do is you could say, well, I'm just going to go ahead and compute d dt. So what's d dt in this case? D dt, and this is like the route that you take towards proving uniqueness, is going to be um, u sub t u sub t plus u sub x t u sub x dx, right? And this is equal to the integral from 0 to infinity of u sub t u sub t minus u sub xx, right? dx, if I do the integration by parts, and plus u sub t u sub x evaluated from 0 to infinity. So I know that this goes to 0, right? But now I have the boundary terms, right? And I know that in the limit as x goes to infinity, right, I'm always going to have 0. So I only need to worry about minus u sub t 0 t u sub x 0 t, right? And so this immediately tells you that if both of these things are non-zero, which they are in this case, then you're always going to be flowing energy into the string, right? So yeah, your intuition is right. As long as both of these elements in the boundary term are 0, then essentially I'm sorry, non-zero, then I'm going to have an well, it not necessarily unbounded energy, right? But I'm going to have non-conserved energy, right? It depends on what these functions are as to whether you'll have unbounded energy or not, right? Because you could have, a positive flow of energy, but it could be decreasing over time, and then, you're not going to get
Could
it unbounded. Does that
could
make sense?
yeah, could you take it one step farther and know that u is equal to like t minus x for this problem? Because I feel like the just knowing that the energy is changing is a little unsatisfying. I want to see that it's always increasing, and I wonder if maybe we can see that because we actually can know what these derivatives are in terms of like f prime.
Right. So you're saying for this particular problem, right? I mean, you can have many
Yeah,
different boundary conditions, right? But here, right, u sub t 0 t is equal to h prime of t, and what u sub x 0 t is in this case, you need the full solution in order to get this, right? So
yeah, but
I can't
we
go
have
farther
the
just given the IBVP here. I need to, I need to work out what the solution is in this case.
but
So,
we have that it's like f of t minus x, right?
right. And so you get what, minus cosine of t minus x. And this is just going to be cosine of t minus x. But of course, x is 0 here, x is 0 here. So yeah, so we get that it's cosine squared of t. So it's increasing indefinitely, right? Or it's non-decreasing indefinitely, right? But you
Oh,
could have situations where these combine in a way that you get a periodic function, and so it just goes up and down indefinitely.
Do we
So
have to distinguish when we're talking about why the energy, like if the problem comes up and asks, why is this energy increasing, or like, why does it diverge? Do we have to distinguish between this boundary condition adds energy to the system and there's resonance with this forcing, et cetera? Like, because there's not really resonance here. It's just that we're always adding energy with sign, right? On the boundary.
Right.
So do we have
Yeah.
to distinguish if there were to have been resonance? Do we have to explicitly say resonance, or can we just say these conditions add energy to the system?
Yeah, it's fine.
Okay.
The latter is fine. Yeah. I mean, we haven't talked a lot about resonance and harmonic oscillators in this class. Yeah.
Yeah, I guess I'm not really seeing intuitively why the energy is growing without bound. I mean, I see it obviously through the calculation, but I'm used to looking for some sort of resonance or growing amplitude with time. And in this case, at any given spatial point, it's just a sinusoidal function. So it doesn't seem like energy is flowing into the system. It just seems like it's.
I think the resonance perspective is more for like a forcing term on the entire domain.
Yeah. Yeah, it would be if h of t was on the right-hand side of the PD rather than a boundary condition. I guess I'm just not used to looking at this way.
Yeah, so it's important to remember that the position of the string and the energy in the string are not, they're not one and the same, right? So I think you're thinking, well, the string is going up and down like this. So on average, the position of the string is 0. Therefore, why is there energy in the string? But as I was saying, the displacement of the string and the fact that this is propagating like a wave means that I simultaneously have kinetic energy and I have potential energy in the string. So any deformation of the string, right, because of the tension properties of the string, are going to give me a positive energy, right? I mean, the energy can only be non-negative, right? And so if it's displaced from equilibrium, that's potential energy. If it's moving, that's kinetic energy.
Well, yeah, I guess I would think about
Sine
integrating over the. Oh, go ahead.
Well, sine creates movement and displacement. So yeah, that's why.
I guess I would think about integrating over the squared amplitude, but that almost makes me feel like there should be infinite energy in the system immediately.
Yeah.
Or at least not that it should be like monotonically, or maybe not monotonically, but like almost monotonically increasing with time.
Right. Yeah. So,
Well,
but remember that there's nothing over here that's providing energy, and so you're only ever integrating the region of support of the problem, right? And the region of support is growing over time, right? But here you have basically the energy is 0 over here, right? The non-zero contributions are over here, and that's
I think that's the part of the perspective I was missing, is that the region of support is growing with time.
yeah. Okay. Cool.
So we concluded that it has to be always increasing, right? Because more generally that u of x, u sub x is going to be like negative h prime of t minus x. And so that product will always be positive when we substitute it in.
Right. I mean, you can have boundary conditions that suck energy out of the wave equation. I think these are like sort of you can have a flux boundary condition that removes energy. So basically any displacement of the wave would just be, any displacement of the position would be.
But that would require left flowing characteristics, right? So we would need some initial conditions or something.
Right.
In this
So you
case,
would have no forcing on the boundary, but rather you would have some initial displacement on the initial condition, and then once you hit the boundary, you killed the energy there, right? But even in that case, you would have energy, propagating rightwards, so you probably couldn't suck all the energy out. So you would need 2 boundaries right, in that case, in order to have energy go all the way down to 0. Or if you have damping in your string, right, like you looked at in the uniqueness problem in the homework, then the damping will eventually remove all the energy from the string. Okay. So yeah, so we're at 12:25 now. So I'll probably call it good there for today. There's a part D of this problem that I was going to get to. I'll just write it here, right? But we won't. I won't stay on to solve this. But it's essentially just prove uniqueness of solutions to the IBVP using the energy argument, and assuming sufficient smoothness and boundedness. Well, let me say integrability. Okay. All right. So so I'll just share that document with you that provides that. I also want to emphasize, like, yeah, I went over this problem in review, right? But basically anything from the homework or the lectures or the book chapters is fair game, right? And you shouldn't expect carbon copies of problems that we've done. They'll, the exam problems will probably be some, slight interesting extension at least of problems that you've already seen. But in my experience, the best way to prepare for that is just to practice lots of different kinds of problems. So as I said, look back at previous prelim exam problems. I'll share some sample problems from past homeworks and past exams in this course by email. I'll send those like in a couple minutes. And yeah, I mean, if you have any kind of last minute questions before the exam, you can shoot me an email and I'll do my best to answer by email. Yeah, hopefully this gave you a chance to practice. So I suggest, practicing more over the weekend. Any parting questions before we conclude?
I have a question.
Yes.
In all of the quarter plane problems we've done so far, those constant of integrations we get, they always end up canceling. Is there some kind of like Neumann boundary condition that you could have that would cause that to not happen? And then your final answer would have some kind of arbitrary constant in it?
Yeah, I think that was the point maybe of the homework problem, is that you basically just lose uniqueness for some forms of boundary condition. I don't know that that's always necessarily in the form of having an additive constant that's non-specified. You could also have, some contribution from a homogeneous function that's not the homogeneous solution that's not specified. But yeah, certainly you could build an IBVP with a boundary condition that has non-unique solutions, for sure.
Okay, thank you.
Yeah.
But wouldn't it not be a constant because we have the initial condition, like the initial position, I guess? So like that's not integrated, or that's not differentiated, so we would need the constant to be not there.
Yeah, I mean, I think you're right. I think the form of uniqueness would come down to an additional function.
Okay.
I'm trying to think if you could cook up a, yeah, because if you have the initial position, I don't see how you could let a constant be free. Yeah. I will say that there can be non-unique solutions. And I'm not sure if that's necessarily, as you say, going to be, because you have that constant be free. You should expect to always kind of be able to cancel that constant, I think. Okay. Any other questions? Okay, good.
Do you care if we ask about this energy argument problem? I guess I'm just curious if we have to do anything at all with the boundary condition, since obviously when we do the difference, like define V as the difference between our unique, then we don't get a boundary condition, but the boundary condition doesn't show up at all when we define energy. Or I guess it does, never mind, it does when we do the integration by parts.
Yeah, I mean, as you should have found, right, in the homework problems, when you're using the energy argument to prove uniqueness and you do this integration by parts, then the boundary conditions are going to show up, right? But remember that when you compute the energy for the differenced problem, everything should be homogeneous, right? So remember, the energy that you're computing when you're proving uniqueness is for, like W equals U1 minus U2. So your IBVP should just be like the homogeneous version of your original IBVP. So if you have some initial non-trivial position, velocity, or forcing on the boundary, that all should be zeroed out by taking this difference, right? And so then when the boundary terms come up from integration by parts, those should be zero, typically. I mean, we saw some mixed boundary conditions where those don't zero out, but they should be non-positive at best.
Yeah, thank you.
Yep. But that, if that doesn't happen, then you can't prove uniqueness.